Hello students, welcome to the class of Digital Signal Processing, and today we will proceed on further with our journey of Fourier analysis. We have talked about various scientists, great scientists who have contributed to this Fourier analysis. We have talked about the applications of Fourier analysis, and today we will delve deep into the complex exponential, which we already started. But let's go again once through that. So first of all, we said that any oscillations can be represented in terms of circle. Why we are saying this? Because what we mean by oscillation here is that it is starting from a certain point and reaching that point again. So we can represent that with the help of a circular motion, right? Now, this circular motion can be represented in terms of sines and cosines. Why we can do that is, see, this green portion is your sine and this blue portion is your cosine. So if you take the coordinate axis, the complex reference or the complex reference of the coordinate axis, this vertical line is your imaginary part, and the horizontal line over here, this line, this is your real part. So this is your real part, this is your imaginary part. Now real part is uh, on the real part, you have the cos omega t, and on the imaginary part, you have sin omega t. Now, these two have been combined by Euler into exponential form, that is e to the power of j omega t. And this is very, 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 very important that you remember e to the power j omega t is equal to cos omega t plus j sin omega t. Now, first I related cos and sine with e to the power j omega t. Now the question comes, how is this related to circle? Now, if I say that this position, this horizontal axis is cos and this vertical axis is your sine, or you can say the real part and imaginary part, then if you find the modulus of this, that means you want to find the radius of this circle. So in the radius of the circle, or let us once do this in a better way. Okay, so if I draw this, if I want to reach this point, so I have to move this distance and this distance, or in other words, you can move this distance. Now this I am saying is cos and this I am saying is sine. If I take this angle as theta, then this is cos theta and this is sine theta. And if I directly want to reach here, or if I want to find the distance of this point, what I will do is modulus I will take, or you can say we will use the Pythagoras theorem, cos squared theta plus sine squared theta, that will give you 1. As here I have not taken any value for how much distance is this, so I am taking it 1. So what is this? The radius is unity. So this way if you move, then basically this angle, this theta is your angle and this distance is the radius. So that is why we are representing e to the power j theta in a circular motion. This is the reason we are representing it in a circular motion. Now, why we are using complex exponential when we had this cos omega t and sin omega t? Because it makes trigonometry turns into algebra. And when trigonometry turns into algebra, the computation is becoming easier. Suppose here at this point, let me take another circle. Okay. Now, if I draw a circle again, I will say at this point on the circle is not drawn very good manner. Let me clear this. Okay, now this is a circle. Fine. Okay. And then I draw a line this way. So this line will change everything, right? Let me take that other line also from here. Now this is a perfect circle. Okay. Now let us see. Now from here at this point, if you are at this point, say at this point, and here the angle is say omega. Again, you are moving with the same angle omega, same distance omega you're moving. Now this, if I am representing as x of n in discrete time, then this is my x of n plus 1. How? Let us see this part. So if I represent x of n as equal to e to the power j omega theta, and I want to calculate x of n plus 1, right? This is say e to the power j omega n. Sorry, this is not theta over here. This is e to the power j omega n. Now, if I want to write x of n plus 1, what I need to do is e to the power j omega n plus 1, right? Now, what is this? This is can be written as e to the power j omega n into e to the power j omega. So, what you did, you have just moved an angle omega. So, this is written over here that why we use complex exponentials here is that phase shift becomes simple multiplication. So simply you are multiplying this e to the power j omega, means it is becoming easier to handle. Now, if it was written as cos omega n plus j sine omega n, in that case, what will happen? If this is your xn, and if you want to find out x of n plus 1, means the next point, then you need to know the whole algebraic trigonometric formula over here, because it is becoming cos a plus b, and again this one will become sine a plus b, because this you will write as omega n plus 1. So you need to remember all the big formulas, and also the statement will become large, and you will have difficulty in understanding. But if you see here, then this is what that you have shifted. This is becoming just that you have phase shifted it, and in terms of mathematics, you are multiplying it with e to the power of j omega. This is the advantage of using complex exponential. Now, the complex exponential has three parts, that is the frequency, initial phase, and amplitude. You have to keep in mind this frequency is the unit of this frequency is radians and not radians per second. Also, the unit of phase is radians, and amplitude as usual, whatever you are measuring the type of quantity, the amplitude unit will depend upon that. Now, the major thing is that there is a difference between continuous time complex exponential and the discrete time complex exponential. This difference comes as a result that you cannot have the discrete time complex exponential cannot be periodic for every omega, as in the case of continuous time complex exponential. So this is a very, very important point that you have to remember. So discrete time complex exponential is periodic. Discrete time complex exponential is periodic only for omega, which is integral multiple or rational multiple of 2 pi. Otherwise, it will lead to a phenomenon that is called aliasing, which you will see right now, multiple of 2 pi. So what I mean to say by this is that suppose you have this signal xn, you have this signal xn is equals to e to the power j omega n plus theta, and you want to check the periodicity. So what is the condition for periodicity? X of n plus n should be equal to x of n. This is it. If I write x of n plus capital N, what will I do? Is equal to e to the power j omega small n plus capital N, small n plus capital N plus theta, right? Plus this theta. Then you are closing it. Now what you can write this part? You can simply multiply it and write it, right? E to the power, e to the power j omega n into e to the power j omega capital N into e to the power j theta. Now this should be equal to x of n. That was what? E to the power j omega n into e to the power j theta. So these two gets cancelled with these two on the other side. And this one, e to the power j omega capital N, will be equal to what? 1. So e to the power j omega capital N is becoming equal to 1. So if you take the mod of this, then n, omega n should be equal to, this is 1. That means it should be equal to 2 pi. Means that if you take cos 2 pi plus j sine 2 pi, only in that case it is going to become 1. Suppose you take cos pi, it will become minus 1. So you take the mod of this type of multiple, only then it is going to become equal to 1. So it has to be a multiple of, omega has to be a multiple of 2 pi. From here it comes that omega is equal to 2 pi by n. Now there should be an integer over here so that it becomes the periodic. If it is something else, it is not periodic. So that is the reason, that is a very, very important point that you have to keep in mind, is that continuous time complex exponential can be periodic for any value of omega, whereas that is not possible in case of discrete time complex exponential, because discrete time signals are available only for discrete values. So you cannot take any value between 0 and 1. Suppose I am sampling it at the rate of 1, then samples at the rate of 1 per second, then I have taken this 0, 1, 2. In between, I have not taken anything. So if you write, if this value is coming in between these two, then in that case, there is nothing to be taken from here. So in that case, it is not going to become periodic. Another way of seeing this is moving inside the circle. If you are moving in a circle, see over here, again the same type of movement if you see. If I started from here, say, I've moved here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and then I move to this point again. So after 12, I have reached the starting point again. So omega will be coming equal to 2 pi by 12. But if I make this angle bigger, this was say for certain angle. Now if I make this angle bigger, so I go from here to directly this point, then this point over here, then this point, and then again this point. So I took just 4, right? But again, if I take only 2 points, means I'm going from here directly to this point and then coming here. That's okay. But now if I am increasing the speed more, then what is going to happen? Now we are not going to become periodic. Neither we are going to become periodic, nor we are going to reach that same point again. That is the meaning of saying periodic, right? So what is happening is that we will be appear to become slower. So let us see this in this video. I'll play this video for you. You could see for yourself what is going to happen here. Yeah, how fast we can go. So this wheel is turning. This is a 4-spoke speed. Now see, as the speed is increasing, the wheel turning is increasing. But at a certain point, you see now, it is starting to move in the opposite direction, right? At some point, it becomes stationary and then it again started to move in the opposite direction. So what happens is that when you increase that value with more than 2 pi, then it will appear to move in the opposite direction. So if I say this was my circle, right? In this circle only itself, if we see it, okay. Now if I am moving, say here I was moving more than 2 pi, that means I will go from here and then I will come at this point, means I have already covered one oscillation and then I am at this point. But it will appear as if I have moved only one oscillation. Okay. Now if the other way of seeing it is that I am moving in the opposite direction. Fine. So this is the thing. This is the thing which you saw over there, that the speed, if you're increasing, then you are never reaching at that point. One thing is that, and you are appearing to move slower in the opposite direction if you take more than 2 pi as the speed of this your motion in that case. So this problem is called the problem of aliasing. Fine. Now after this in your syllabus, you have all the discrete time cases, but you have the CTFS also. But in actual Fourier analysis, you deal with both the continuous time and the discrete time. So basically, we have the continuous time Fourier series, continuous time Fourier transform, discrete time Fourier series, and discrete time Fourier transform. The other two that is mentioned over here, that is DFT and FFT, these are basically the computations are becoming easier by using certain symmetry and periodicity property. The computations are becoming faster. That is it. And I will tell and make you understand how DTFT how becomes DFT. We are sampling the DTFT itself and making it DFT. That is the major difference between DTFT and DFT. And between DFT and FFT, that is the computations. You are extracting the periodicity and the symmetry property. So first, one thing that you have to understand here is, or you have to keep in mind is that when you are analyzing the signal in time domain and frequency domain, there are two things. So if in time domain, the signal is continuous, its spectra in the frequency domain will be aperiodic. Aperiodic means non-periodic, okay? If the signal is discrete in the time domain, then its spectra in the frequency domain will be periodic. If the signal is periodic in the time domain, then its spectra in the frequency domain is discrete. And the signal is discrete in the frequency domain. Now, if it is aperiodic in time, then in case of frequency, it will be continuous. So instead of keeping all this in mind, just keep the above two: continuous, aperiodic, discrete, periodic. Now, if you see this portion, there have been certain questions. So I am just making you all know this point. Now, this is here the time, and this is the frequency part. Here you see, this is continuous in time, continuous, and Fourier series. If you remember, I said about Joseph Fourier that he said his statement was that any periodic function can be represented as sum of sines and cosines. So he has, till him, it was Fourier series. Now, after the Dirichlet's condition, we got that any non-periodic signal can also be represented as Fourier series, or you can say Fourier transform. The other name given to it was that Fourier transform. So this signals in this case, CTFS case, in the time domain, it is continuous and periodic. And when it is continuous and periodic, that means the spectra is, what is the spectra? So continuous will become what? Aperiodic, and periodic will become discrete. So discrete and aperiodic. Now this side, continuous and aperiodic. So it is going to become, so aperiodic will become continuous, and continuous will become what? Aperiodic. So getting the point. So continuous is becoming aperiodic, and aperiodic is becoming continuous. Now this part, discrete and periodic. This is discrete. Fourier series. Series means we will take it periodic, discrete and periodic. So what it will become is periodic and discrete, right? So it is what it is. Discrete and periodic will remain discrete and periodic. Now if you take this one, discrete and aperiodic, then it is going to become continuous and periodic. So when you write the formulas for all this, you will understand this more clearly. Okay, now let us see the first of it. That is what we have to study, that is DTFS. Now this is called discrete time Fourier series. Now questions and how you have to do here, the mathematics we will deal with. So today I'll just give you the formulas with which you have to deal with in this case of this discrete time Fourier series. So discrete time Fourier series, so as the name is given, discrete time, so the signals will be represented as x of n, right? The signals will be represented as x of n. Now this x of n will be equal to ck e to the power j 2 pi k n by n e to the power j k e to the power j 2 pi k n by n. Now this ck is the Fourier series coefficients. This ck is called the Fourier series coefficient. So in certain questions, you'll need to find out the coefficients, the value of Fourier series coefficients. And the very important point, that is required over here is that this k is ranging from k equals to 0 to n minus 1. This pKs are called the line spectra. Okay, so we will do the next part, that is the questions in our next lecture. Let me stop here, and we will be dealing with the exact questions, numerical problems in the next class, and I will be explaining this in more detail. Thank you, everyone. Let's meet in the next class.